Hello, good to see you all. It's a cool intro. Today we're going to discuss some new features. These are big features, but they may be very simply used with your application. And the hope is new Java features can give your application a second breath without changing your code. That's a nice idea. And why do we need it, right? We want to utilize resources. We want to save spendings on our infrastructure. So that must be useful. But sometimes, if you simply change something and you don't check what has changed, you may see unexpected results right on your production. My name is Dmitry Chuyko. I worked at a company named Bellsoft, and I contribute to OpenJDK, which I'm happy to be a part of. And the company releases its own distribution of OpenJDK called Liberica JDK. Maybe you know it as the recommended JDK for Spring Boot. And also we release our own distribution of Graal JIT, Liberica native image kit, which I will also showcase today. I will collect results from JDKs, from native images, from Graal JIT. And also we have our own basement, Alpakita Linux, and you can find out more on our booth. Welcome. So, yes, we contribute. And as I've stated the problem, we develop applications. Someone, us or them, deploy those applications. Someone, us or them, monitor those applications, deliver some warnings, urgent nightly calls. And someone pays for the running applications. Of course, applications help business to earn money, but business also spends money for the infrastructure, for development. So it's nice to spend more to save. To spend less to save more. No one shouts. And to avoid such situation as huge underutilization of resources, which typically happens, and it happens more and more frequently, especially in environments like managed Kubernetes. Because a lot of things are just done for us automatically. We use out-of-the-box solutions. We don't care about fine-tunings. We need to deliver our products faster. So we end up with this. At the same time, some load spikes happen. And during load spikes, all unexpected effects that were not there for ages, they just come and strike us very badly. And we start optimizing, right? If we start optimizing blindly, let's take some recipes from somewhere, let's just enable new features and expect some profit. Those assumptions may be entirely wrong. Instead of having some profits, we may have some losses, but we may see those profits as well. Well, I'll experiment with my, maybe your favorite application. I've recently updated to the latest version. And also, we have new shiny JDK released out, JDK 25. So why not take JDK 25, but also some other JDKs or older JDKs, and also and get those experiments. And we'll take a new Graal VM 25 as well. And the experiments with such Spring Boot application started with trying to scale it horizontally properly, to find out the golden pod size for this application within the same available resources, to maximize the number of operations that it can perform without losing, without behaving bad in terms of response time. And those experiments led to using such kind of port. We can just run such application on such machine or in such container. Just use like some memory. Maybe that's not even the right ports here. Looks like it should be 4 CPU and 8 gigabytes. But it's approximately the same result. So if we have multiple replicas on the same machine and we properly divide the machine, we'll maximize the throughput, for example, and we have 20,000 operations per second from this application on a single machine, just using multiple replicas. But let's try to optimize a single replica, or decide if we need, if we maybe need a different pod sizing, right? Getting back, we prepare that container. We can do it in a simple way. Who does that? I know you have lunch in your hands, but you can raise your lunch. Yes, yes, thank you. You're so honest. Don't do that. I have separate talks about making it in a different way, but here, let's see at one of examples of a better Docker file, if we use Docker files. Even in this Docker file, we have a couple of nice pills for our JVM, and it will probably give us a reward back. It will reward our application when we have given it those pills. Who can see what are the pills? What are the dopes? Oh. Max RAM, yes, memory. Thank you. JVM, please eat the memory. That's the major one. Otherwise, it will use still less memory, and it will really help our application, because it will help garbage collection, obviously. What's the another dope? Layered image, but that's not the dope for the application. It's kind of a dope for our container management system. Yeah. Yeah, extracted layers. Again, yeah, you're getting it. But the thing is, at the last line, we use system class loader, and it helps us to load classes faster. No, not a big deal, but it helps us. All right, and we can get such things for free. Just we don't need to write Docker files at all. And we will have some dopes automatically by using buildpacks. You probably have attended some talks about buildpacks on this DevOps, great deep dives. It's an easy way to take them. Just you don't have to think about things that happen. You just have to test it, of course. Maybe sometimes you need to tweak it. We have some nice tweaks we can use. But basically, it's very simple. You don't need Docker file. You don't need to think, well, hard about your Java options. The memory amount, the heap size will be calculated for you. Maybe some other options will come into play. That's nice, JFR settings. But we'll start creating a load for this application. In like today's example, let's limit it to 500 requests per second. And it happens on a small machine, like this machine in a mode prepared for measurement. And we'll be chopping the cow, the bull. Have you ever chopped the bull? Yep, me too. I only, consume some parts of it. But we'll chop our application. Hedge. So what happens here? We see how application starts and begins to work. It's a fixed load, so we have the same amount of requests per second. At first, we have no load, of course, because we need to start our applications and an application and wait for it to be ready. So that's the very first part called startup here. You see on the left chopped plot, we have two lines, CPU and memory. So two scales are combined together. I hope it won't confuse you, because it's easier to compare side by side if we plot them both. So red line is CPU, and the scale is on the left, and the blue line is memory, and the scale is Y scale is on the right. So we have the initial phase when application starts. We see CPU raised, we see memory raised. Then in the experiment or in our real production environment, test environment, we had some pause. We need to finally switch it on, let it work. And we put some load on it. And that load is also divided into parts. The observed results are divided by two parts, but also we can measure those parts separately. First part is warm-up. We need to reach peak performance, and it takes time. So how much time does it take in this example? Shout a number.
60 seconds.
Yes, about 1 minute. And in real systems, it's much worse. It may be 60 minutes, not seconds. And this part is important. And we would really like to get rid of it. What's even worse, during that warm-up phase, we spend additional resources. That means for that relatively short phase, if we compare it to a typical infinite lifetime of the application, we spend some resources and we require them. So we require port sizing that will provide us those resources. So we pay for, during the peak performance phase, we pay for resources that we don't use. Well, we might accidentally start using that, right? Because we have that headroom. And imagine we scale depending on the number of incoming requests per second, right? So we limit our application, but sometimes we still can get a higher load, or we can get some actions in our application that require more resources. So that's not such a bad thing, but we must remember it. So let's collect the bullback. That looks nice. And those are tricky plots, the second and third plot. It's in fact cheating, because if you look at time, it's not in fact time, especially if we talk about first second. It's just a set of groups when we try to average the response time. We can calculate the response time or some percentiles of response time. In this case, let's look at P99 percentile, because there are not too many data points if we select about 1 second chunks. But it is more or less close to what the real plot looks like. It's just easier to construct. And if we look at the very first second, or a couple of seconds, the actual values of response times will be around like 700 milliseconds in this case. So this is just a default setup. We run server VM with G1, so we have quite bad response times, but we warm up, and it's fixed. So let's try to apply some dopes. Let's switch to a garbage collector that existed before G1. Maybe it will be better. And it's already known from previous experiments with it, with application, that serial really gives good results. This is for this workload, because the working set is small, so we don't experience bad old garbage collections. So we collect young generation, and it's kind of fast. So you see, this plot doesn't change much, but we we actually save some memory here. How much? Yeah, half of memory. It depends on how do you apply those savings, right? We can measure Java heap, for example, or we can measure Java heap after collection, right? So that's a true memory occupied by our Java objects. But we also have some overheads for the garbage collector itself. We have native memory, many things. So in general, monitoring, looks at all those heap metrics, just to see if there are spikes or whatever. But we actually need this, simply a view from an operating system perspective. What happens with this process? How much memory does it take? And if we look at roughly latencies in dynamic, we may see that, well, it becomes better. You can see it visually, right? Less big spikes, less spikes. And if we measure client latencies in that warmed up state, we'll see some better results. Okay, let's try another garbage collector. New shiny generational ZGC. Yes, it is not a terabyte heap, right? But we still can enable it. So what would you expect? Well, at first, it is a collector designed to work with large heaps. And it honestly trades memory for latency and other metrics, right? So it's up all the memory that it can eat up. But instead, it will provide us something. Yeah, you see here, like it ate up 7 gigabytes of memory. The application, it's 7 gigabytes of memory. If you look at such plot, there's no big difference, right, in response times, but they're somehow averaged. But if we really look into what happens, the client latency is much smaller if we look at the warmed-up phase. So we have improved it both with serial and with ZGC. But with ZGC, we've traded it for the way it works, and it just takes all the memory. It may be not so. There's a switch that recommends it to use only a certain amount of memory. But with serial, it's even simpler. We just see the result immediately. And we also have improved startup in case of serial. Not on a big delta, but it's still very nice to see. And you know that serial garbage collector sometimes is enabled automatically if your machine size is small, but that will probably and likely change in upcoming JDK releases. So G1 will be the one collector that rules them all. And it's expected that it will be not worse than serial, or at least not significantly worse, which means we can observe predictable results and understand that the difference is somehow constant or the ratio is somehow constant. So I've mentioned that we may target the amount of memory used by GC, but we also can target pauses, for example, in case of G1, so we can make the results better for G1, right? It's not necessary to replace your garbage collector. You can try to tune it, especially if you only will use one flag for tuning. And we can also influence some other metrics that will probably change our latency results or our consumed memory, of course. If you use, for example, pre-touch, that will influence both. But why don't we simply replace the entire VM? And in fact, with a full JDK distribution, you get 3 JVMs. You get server JVM, you get client JVM, and also minimal JVM. And yes, minimal is for minimalistic kind of IoT deployments, but client is kind of useful in cloud. We can throw it in this experiment and try to compare what results does it give. So what client does? It also allows us to use G1 or serial, but it limits the amount of resources spent by JIT compilation because we only use client compiler and some other changes. But with the latest stuff that I've tried recently, it's interesting to see that the application become unbalanced. So if we wouldn't experiment, we won't see it probably until someone will report a bad behaving instance in production. You see that the latency grew up very dramatically. But actually, if we lower the load that comes to this application, it won't be that different. So the response time will be worse, but not an order of magnitude worse. And we'll see some numbers. So it can be fixed. But if you really lower the limit for requests, for request rate, incoming request rate, what does it mean? If your pod can accept less requests per second, and you still need n requests per second for your system. Yes, you need more pods. And if you need more pods of the same size, what does it mean for your business? Yes, it will spend money and it will ask some questions. So with client VM, there are nice improvements we can get. The actual warm-up time till those not so good metric values is much shorter, much shorter. It's some seconds, not tens of seconds in the case of this application. We do use less memory. We have some savings here. We can use smaller instances. It's not typical, like you see the scale, the difference is not in scale of, for example, cloud instance sizes, right? So they differ much more. And even the weakest ones probably have enough memory for such application. But still, it's nice. But the maximum request per seconds dropped more than twice. So we need 2x more instances. And as I said, take the hit for your latency, for example, or double your fleet, right? So what can we do beyond it? Well, let's take another VM. Let's remove the JDK and use Liberica native image kit with Graal VM as a JIT. Hopefully, in this experiment, it doesn't warm up itself. We can enforce that. But still, you see the warm-up is longer, so probably the compilation takes more time. So we are shifted right, which makes us wait, spend time, which we can't restore. And if we compare latencies, you see it also becomes, well, worse during the longer warm-up phase. But in the end, we had about the same peak performance. For this application, these compilers, about the same. But the latency is actually worse, but it still can be considered okay. Maybe we just need to lower the load a little bit, right? It doesn't look too scary. But there's no probably reason to switch, right? So what can we do else? Finally, instead of using Graal as a JIT, we can use it to produce the code ahead of time and use that compiled machine code and skip that startup phase and the majority of warm-up phase entirely. We still have some initialization, right? The application starts normally. Maybe some simple initialization happened ahead of time, but most of it still happens in runtime. So we have some spike in the beginning. But you see, we do use slightly less memory, so we compare serial to serial GC. And well, CPU usage, it depends. In this example, it is about the same if we compare CPU usage after warm-up, in case of the regular JVM, and the CPU usage in the main phase of Graal VM, right? But we don't have such big difference. And the main thing here is that we don't have those left parts. We have peak performance from the very beginning. Almost, but this almost is really a fraction of the result. So the results are very stable, consistent, and we can easily scale up and scale down with this technology, which is very important. If we start a pod or many pods, we don't have to wait. We don't have to invent any solutions how to start them ahead of time, how to warm them up. We just get the performance. And it's predictable. We can test it. And we can be sure that, yeah, that's the technology that covers this scenario. So what we've got in the result? Stable CPU consumption, startup, which is instant. The warm-up, as I mentioned, we still have some initialization, but we have peak performance from the start, so I would say it is 0. The footprint has decreased, but latency is slightly worse, not slightly, like 2 times worse. And if we imagine a limit of 100 milliseconds, we're above the limit, obviously. So we'll have to do something to improve latency. For example, switch to parallel GC in case of Liberica native image kit. Well, another great improvement in OpenJDK is compact object headers that are not yet enabled by default, but they are no longer experimental in Java 25. So you can simply turn them on, and for every object, you will save the payload that's been wasted for its header. And you see on some architectures, it's a quite big value. And it is so for any size of object. So for every object that has a header, we spend that much. Now, we store that objects in Java heap, which means we spend memory for storing headers, and if we have smaller headers, we spend less memory. But you won't see it on these plots. Like in that latest experiments, the loads seems to be on the edge. So if something slightly changes in the JVM, so you'll have slightly worse throughput or latency, and you get fixed load, you probably will experience big penalties. So you still you don't have any spare second or fraction of a second for a VM to correct itself. So you see what happens. Like the latency go bad, and you can't observe those differences in heap. Well, in fact, if we lower the load, or just take JDK 24, for example, and all the Spring, you will observe the difference. And it's an entirely different picture, right? That means we have passed that point, that edge, and switched to the mode where we have some headroom. And the JVM can struggle with the load, the application can struggle. And you see that it can consume significantly less resources. So you see here, like in the case of such application, we save, well, about how much? 20% of memory or so, right? So just like predicted. But if we are unlucky and we haven't tested what happens, or we haven't tested what happens if we exceed the headroom we preserved in our application, well, it may go wrong. Another great technology that took such a long time to be implemented in OpenJDK is ability to use virtual threads. But to use virtual threads, you must explicitly say, hey, these and those threads that I create are virtual. So how to enable it automatically? Well, in fact, some JDKs exist that try to do it automatically, but framework does that for you. At least for some parts, for example, for incoming connections, when you handle them, you can ask your framework to use a different thread pool that will use virtual threads instead of platform threads. So major problems have been fixed till JDK 24, and now we have JDK 25, when the technology is quite mature and it's supported by frameworks. I can simply use it, enable it. Of course, if we create or create threads in our application, or we don't really like async handling of results, any async programming, or we use some thread pools, we can switch to virtual threads in our code as well. And in any case, virtual threads are threads, so they have some imminent problems of being a thread. Just program them correctly without deadlocks, without extra locks, etc. So we'll use same setup with serial GC and compare what happens if we just switch on virtual threads for incoming connections pool. You see there's no a big difference, right? There's no intense calculations or so. And we actually don't spend too much memory. Because you can expect some savings from this thread pool if its default size is up to 256 threads, and each thread has a stack of half of a megabyte or a megabyte. How much would you expect to save? Like over 100 megabytes. But that's not the case here. We still actively use the heap, so we don't see it from this external monitoring. But if we look at latencies, you see, again, visually, there's a difference in spikes. So the pictures on the right look probably better, except the P99 mock-up for the end of the warm-up phase. But we are definitely interested in the steady state. So that's how virtual threads were enabled. And indeed, it even improved the warm-up, and the latency is better. So the same garbage collector, we simply enabled one property. Here's the pill, take it. The framework did it for us, enabled virtual threads. JVM did it for us. Good for application. Well, also new technologies, or same known technologies with a new name and new functions. AUT cache in Java 25. AUT cache went beyond AppCDS, so it has new data stored in it, and it has new command line interface, which I find more convenient. You have to take less steps to create and use your AUT cache. But there are, of course, some trade-offs, and we'll look how it happens. So I won't describe what happens with your AUT cache, right? There are dedicated talks about how it works, how the data is stored, how startup happens. Just look at the data here. You can see that shorter warm-up phase, right? Can you? Right, probably yes. If you look here, again, there's no big difference, but we have chopped out or slimmed the very initial peak. Because we have created in this first experiment, so there are two experiments. They depend on the point when to create the AUT cache. What are the options? Obviously, first, when the application has started. What's the second option? Any point beyond that. Because we, for example, store some information about method profiles. And methods profiles are obviously more interesting on the longer run. So we can start with that initial point when the application has started, the first chop, right, of the cow. And we can use information available at that point to make the AUT cache. And another approach, right, is to perform it after the warm-up. We know when the warm-up happens, so we say, okay, at that point, we will create the cache, because it's warmed up already, right? That makes sense. And you see again, well, for memory and CPU consumption, there's still no big difference. And for observed response times as well. But what's even worse, for that scenario when we wait for the warm-up and after that we create the cache, the latency measured for the tail part of the lifetime is worse. That means we have some big trade-offs, for example. But the startup is better, of course. We saved a few seconds on startup. Well, probably that was a big price. Because we also have to take the over 100 megabyte archive with us. For example, we should put it into our container image and deploy every time. We have to create it during our build. And we also may see some incompatibilities if we want to change settings for the JVM in that container image. Or we will change the hardware where it runs. Well, it may strike us back. Well, anyway, this technology improves. And you know about Project Leyden, probably also been very well covered on Devox. And we can take the EA tool for Project Leyden, the most recent one, and try to experiment with AUT cache that also allows you to store compiled methods. So you can collect the configuration used. You can compile some methods ahead of time and store them into AUT cache and use them on startup, right? Theoretically, it should bring us to a situation when we don't have startup and warm-up almost, right? Because we load everything, memory map everything from disk. It's interesting that it's not true in some experiments. definitely something happens, and there is a difference. But you see, we still spend about the same amount of memory. That's predictable, but we don't have a shorter warm-up phase. And again, this is true for both scenarios of IoT cache creation, right? Though we also get the same or even worse latency strike. And here, by the way, the baseline is the same application being run on the Project Leyden build, not on JDK 25 build. Right, so the overall process is, you should know your requirements. You should not break your SLAs. You should reach your SLOs. And you should work with different tweaks, different options available to you. It's quite easy, but it takes a lot of time, Well, some addition. What happens with all the JDKs? Not everyone is on Java 25, obviously. Well, for Java 21, for example, and below, we have AppCDS. We can use it. We can save some resources on startup. Again, lower that initial, make the initial peak slimmer, save few seconds by a small price of delivering an extra file in your container. We can use JDK CRaC, where we again chop the startup phase entirely, and we can chop some of the warm-up phase. And we simply snapshot the application and restore it back, and we continue running, right? It's available to you with JDK CRaC builds. But also, if we go to an even older JDKs, what do? Probably we still can offer some nice JVM pills for our legacy applications. Just let's take a newer JVM, combine it with the older JDK shell, and get something that can be a drop-in replacement for your legacy applications. And you can apply all those tweaks available in the version of the JVM, which is inside that baby, and you get that newer JVM, and it helps your applications. You can scale Java 8 applications vertically with ZGC for large heaps, right? It's a typical situation because people invent solutions like running multiple instances of the application without containers, just to have smaller heaps, to have predictable or limited latencies. Instead, they could use ZGC, for example. And the same happens with other aspects of application activities, like data compression, cheat compilation. Things that are available in newer JDKs are typically much better than the things contained in older JDKs. And that's what you can get with things like Liberica JDK Performance Edition. And if you want to know more, again, come to the booth, and we'll show you how it works. You see, for application like this, but built not on Spring Boot 3, but on Spring Boot 2, you can observe obvious improvements like memory usage reduction. So please try that. Blame my experiments. You can reach me easily. It's not a problem. I'm here on the booth. I'm in the corridor. I'm on the internet. And thank you for your attention.